a piece of software reached through a computer screen and broke nuclear machinery. Its name was Stuxnet. Its reported target was Iran's uranium enrichment facility at Natanz. Your centrifuges worked in carefully arranged cascades. Those machines spun at high speed, supporting a nuclear program that governments wanted delayed. The reported goal was delay without triggering kinetic conflict. Software offered a covert path. Think of Stuxnet as a precision-guided missile made of code instead of metal. It crossed ordinary Windows computers, searched patiently, and activated sabotage only when the machinery matched. Reaching Natanz was a problem because the facility was designed without an internet connection. The air gap looked like a moat around the industrial network. Stuxnet found movable bridges. It spread through removable media, including USB drives, and through Windows network shares. The exact first route remains uncertain: contractor laptop, infected USB, supplier connection, or some combination. That uncertainty matters. A dramatic lone agent USB story would turn an unresolved path into fake certainty. Once inside Windows, Stuxnet used multiple previously unknown vulnerabilities, an extraordinary technical investment for one worm. 4 CVEs are documented, including CVE 2010-2568, malicious shortcut files. Microsoft later patched that shortcut flaw with MS-10046, closing one route used for removable media propagation. Yet Windows infection was only transportation. The real destination was Siemens Step 7 industrial control software. Step 7 lets engineers program PLCs, small computers that tell physical machines exactly what to do. Picture a PLC as a tireless foreman beside the centrifuge floor, repeating precise instructions. Stuxnet checked for Siemens S7315 controllers arranged in a very specific centrifuge configuration. Most infected computers were stepping stones. The sabotage logic waited for its narrow industrial bullseye. At that bullseye, the worm changed the PLC instructions controlling centrifuge rotor speeds. It periodically pushed the machines far outside normal operating speeds, then changed them again. Delicate rotors endured engineered stress while operators searched for ordinary equipment problems. The deception made the attack nastier. Workstations reported normal-looking readings during the hidden manipulation. The dashboard said steady. The machinery was being driven toward failure behind that calm display. It was sabotage with a forged instrument panel, giving defenders both damaged equipment and misleading evidence. About 1,000 IR-1 centrifuge failures are attributed to Stuxnet during 2009 and 2010. That number remains an estimate, and the exact delay to Iran's program is also disputed. Public estimates range from 1 to 3 years of delay. The operation's reported intent was a 1 to 2 year delay without the escalation of a kinetic attack. Then the precision weapon was found spreading beyond its narrow industrial target and became visible worldwide. In June 2010, Virus Blockada in Belarus identified a previously unknown worm spreading through Windows Short Connect files. Researchers then uncovered its unusual layers: Windows propagation, PLC targeting, physical manipulation, and concealed telemetry. A program built for a tiny target had left enough footprints for analysts to reconstruct its purpose. Attribution came next, and here the language needs discipline. Governments left no public signature block. Reporting connected Stuxnet to Operation Olympic Games, a covert program aimed at delaying Iran's enrichment effort. That reporting described a joint United States and Israeli operation spanning the Bush and Obama administrations. Technical complexity also pointed toward state resources, specialized engineering knowledge, and extensive testing. The United States has never formally confirmed authorship of the operation, leaving public attribution unresolved. So the accurate conclusion is widely reported U.S. Israeli responsibility paired with official non-confirmation. Stuxnet permanently widened the meaning of cybersecurity because its payload ended in spinning machinery. A compromised laptop could become a route into an air-gapped industrial process. A manipulated controller could make a trustworthy dashboard lie while equipment destroyed itself. And a government could pursue strategic effects with software was keeping attribution publicly ambiguous. For defenders, the lesson begins at every bridge across the air gap: media, laptops, vendors, and engineers. Control logic and physical process data need independent scrutiny. because one compromised view can hide sabotage. Industrial defense must compare machine behavior with commanded behavior and verify that healthy screens reflect reality. Segmentation can slow an attacker. Monitoring, removable media controls, engineering workstation security, and change review reduce opportunity. Stuxnet showed that code could deliver physical and strategic consequences once reserved for weapons. It leaves one question still spinning. If Stuxnet was the first widely known cyber weapon, what comes next?